All right, let me try that there. All right, so this is the first part of our electrons and gases unit, and we're going to start by looking at the electrons. So we're in chapter 5 in your textbook, pages 126 to 153. So we're first going to start by looking at light itself, and we'll tie it in with our electrons here in a second. So you guys have already studied light as a wave, and so when it behaves as a wave, we know that this is a repetitive pulsing energy as it moves through space, and these waves are able to transmit energy. Now, this is no longer the only way we think of light, but it's the only aspect that we actually considered before 1900. So let's look at a couple of the characteristics here. Waves have amplitude, and this is the height from the baseline. So this accounts for its brightness. It also has a wavelength, which is the distance between similar points on two consecutive waves, and we will take a look at that in our diagram that we have coming up in a little bit. It is represented by the Greek letter lambda, which looks like kind of like an upside down Y, and its unit comes in some different forms. You have the meter and the centimeter, which we're both familiar with, but we typically use the nanometer, which is 10 to the negative 9th meters. That is an SI unit because it's a SI prefix. And then the last one is not. That is the angstrom, and you may want to make a note of that. An angstrom is 10 to the negative 10th meters. It's kind of one of those holdovers that we've continued to use just because so much of the early work was actually done in this unit, even though it's not officially an SI unit. The third characteristic is frequency, and frequency are the number of waves that pass a point per unit time. This is usually per second. So its symbol is the Greek letter nu, which looks like a V, and its unit are waves per second, which is the same thing as hertz. So if you think about it, 1 wave per second is a hertz. So we abbreviate that as 1 Hz, and sometimes we also refer to it as 1 per second type of thing. We just take the wave part out. Speed is also a consideration when we look at waves. So this is how fast our light is actually able to travel. So the nice thing is that light has a constant speed in a vacuum of 3.0 times 10 to the 8th meters per second. Now, what we were able to do is we were able to take these different pieces and actually relate them to each other, specifically the speed, the frequency, and the wavelength. So if you look, we actually have an equation here, C equals lambda V, where C is the speed of light. Remember, that is constant, and it is constant for all types of radiation, which is not just light, and that wavelength and frequency are actually inversely proportional. So as frequency goes up, wavelength goes down, and as wavelength goes up, frequency goes down. So this actually allows us to solve certain things when we only know pieces about light. So if we take a look at our first example, we're going to calculate the wavelength of light in angstroms that has a frequency of 5.50 times 10 to the 14th hertz. So I'm going to use my equation, C equals lambda V, and I'm going to plug in the things that I know. I know speed of light, and I know my frequency, V. So this is the setup. Okay. Now, when I rearrange this, I do get my, algebraically, I get my wavelength, but notice that my unit on speed of light is meters, so that means that's going to be the unit for my wavelength, 5.45 times 10 to the negative 7th meters. But that's not what the question asked for. The question actually asked it for it in angstroms. So we need to convert that. You have to keep in mind that 1 angstrom is 10 to the negative 10th meters. So it's some simple dimensional analysis. We just take my 5.45 times 10 to the negative 7th meters, or just take the answer as it was on the calculator. You multiply it by 1 angstrom times 10 to the negative 10th. You can see there was probably some things after the decimal, but it ends up being 5,450 angstroms. All right, so if we look at the second one, we can actually also then calculate the frequency if we know the wavelength. So here we've got the wavelength in meters, and that is important to kind of keep in mind. If your wavelength is given to you in something other than meters, just like what we did before with converting it from meters to angstroms, we'd have to convert from angstroms or nanometers into meters in order to get the units to cancel. So again, I'm going to use my C equals lambda V. I know my speed of light because that's a constant, and in this case, I know my wavelength. So I plug those in. I solve algebraically, and I get my frequency as 6.83 times 10 to the 10th hertz. Now let's take a quick look here. You've got a little picture up in the upper right-hand corner there of your notes for parts of the wave. Okay, so if you take a look here, letter E and letter F. This is the displacement from letter A, which is called the baseline, which I know is not labeled, but letter E and letter F are referred to as the amplitude. Okay, that's what accounts for the brightness. How high that is gives you the different brightness of light that we see. Letter B is referred to as a crest, and letter G is referred to as a trough. And the distance from trough to trough, represented by D, or from crest to crest, represented by C, that is your wavelength. All right, so if we talk about electromagnetic radiation, this is all forms of energy that consist of both electric and magnetic fields, and they vary repetitively. So what this does is it gives it wave-like behavior. And this encompasses all energy from radio waves and all the way up to gamma rays. All of them travel at the speed of light, and they vary in their wavelength and their frequency. The one that we're most familiar with, obviously, is Roy-G Biv, which is our visible spectrum. And you can see here, red light has a wavelength of 700 nanometers, whereas violet has a wavelength of 400 nanometers. So we're going to have a higher frequency of light in the violet spectrum versus the red, because red has a large wavelength, so it's going to have a smaller frequency, whereas violet has a smaller wavelength with a higher frequency. And you can actually see that on here really, really well. So I've got my radio waves down here at this end, which have a low frequency, which gives it a longer wavelength. Okay, all the way up to gamma rays, which have a very short wavelength, but a very high frequency. In the middle here, we have our visible spectrum, and you can actually see how small of a portion of it that makes up. Now, but this is not the only way we think of light anymore. We also think of light as a particle. And it all started with a guy named Max Planck. He was a German scientist, and he actually studied light that was emitted from hot objects. So think of like on an electric stove, you have those coils. When they heat up, they turn red. And what he observed was that the color of light actually varied with the temperature of the object. So he came to the conclusion that a hot object does actually not absorb or emit continuous radiation. It absorbs or emits radiation or energy in a packet or a bundle called a quantum. And he said this quantum is the smallest amount of energy that it can be broken into. Just like the smallest amount of money that we can actually have here in the US is a penny. We don't have anything smaller than that. So like when you go to the gas station and they have the price is listed at like 285.9. We can't pay 0.9 of a penny. They just round it up to the next highest one. So what he was able to do is, oops, wrong way. He said that not only was did it exist in these quantum, but the minimum amount of energy that can actually be lost or gained by an atom is this quanta. And so energy, he said itself, is quantized. It actually comes in packages like gifts. So it's very discrete, and you can't like give half a gift type of thing. So he proposed the following relationship between a quantum of energy and the frequency of radiation. So the energy, which is given in joules per quantum, but again, you can change that into joules per mole or joules per kilojoule or kilojoules per mole if you need to. H is what we call Planck's constant, and you can see that there. That is also in your reference folder, along with the earlier equation that we did and this one. And then V here, or nu, is our frequency that we used before. So what this does is it allows us to tie together the equation that we were working before and take it all the way to the energy that that particular piece of radiation actually has. So if I have a beam of light with a wavelength of 569 nanometers, I can actually now calculate the energy. But I have to start first by getting the frequency, which we know how to do. We're going to use our original equation, C equals lambda V. We know C, we know lambda. Now, we can't just put in 569. We actually have to change that to meters. Okay, so we just take 569, and we know nano is times 10 to the negative ninth, and that's how we change it. I know this is not correct scientific notation. Just run with it because we only need it for during the problem. So when I rearrange that and I solve it, I get my frequency is at 5.27 times 10 to the 14 hertz. Now I can use that and my energy equation from Planck and actually solve that. So E equals hv, I'm solving for the amount of energy. H is a constant, it doesn't change, and now I have the frequency. Okay, so I plug in Planck's constant and my frequency. The hertz and the seconds actually cancel out. And so what I end up with is my, and that's supposed to be E, not frequency, but my energy is 3.49 times 10 to the negative 19th joules per quantum. Okay, so at this point you should be able to kind of solve some of these problems that relate to both frequency, wavelength, as well as now energy. We should be able to tie them all together. Now, Planck wasn't the end of the story though. Einstein actually came into the picture. Now, he won the Nobel Prize in Physics in 1921 for this. He is actually the one who expanded on Planck's theory, and he explained the photoelectric effect. And this was the idea. If I have light coming into a vacuum tube, so the idea here is I don't have any other atoms except for the metal plates that are present. He found he could actually complete the circuit. So what it, in essence was happening is the light was coming in and actually bumping the electrons off of the metal plate over towards the positive plate to complete the circuit. So that was his observations, that the electrons were ejected by light of sufficient energy. So it had to have a certain amount of energy. It wasn't just any light, but once we had a sufficient amount of energy, it would actually complete the circuit. Okay, and the energy minimum is different for different metals, which also makes sense. So how he knew this was happening was because we would actually see a current here on the ammeter. And as long as we had, light with a certain amount of energy, it would occur. And if I increase the brightness of that light at that same wavelength, I would actually increase the current with that. So this is what he concluded. Oops, no, I'm sorry. Don't forget his energy minimum. Remember, that is the frequency of light. So there was a specific frequency at which this would happen. And then the current with the brightness, remember, that is the amplitude of the wave. All right, and so this is how he actually proposed that things were related. So let me get my little pen going here. I'm going to use my pen. All right, so what he said was that with any piece of light, you have, until you get to a certain frequency, nothing is going to happen. And then after that point, it's actually going to shoot up. Sorry, I know this isn't the best curve. And then it is going to level off. So the idea here is that we have a certain amount of energy or certain frequency that actually triggers the current, and that it will increase in a narrow band of frequency, and then it will just kind of level off. So again, his conclusions were that light consisted of quanta that behaved like particles, which was a different way of thinking of light. This quantum of light is called a photon, and a photon is a massless particle that each carry a quantum of energy. So this was the little packet that we were talking about before. So he described light as a stream of particles, and this actually led to the kind of the start of the field of spectroscopy. So this is how we started studying substances that are emitted to or exposed to some sort of continuous exciting energy. And the idea here is that each of these will emit a spectrum. This is a unique set of wavelengths that are either absorbed or emitted by a substance. Okay, so if we take a look here, we need to make sure that we understand what we're talking about here. The continuous spectrum is the one that you guys are familiar with. So this is our spectrum of all wavelengths. This is if I take a prism and I just use the lights in the room, it will split it out and I will get the full rainbow. I can also get the bright line or line spectrum, and this is usually what we look at when we look at how energies are changing with things like an atom. This is the spectrum of only certain emitted wavelengths. And what we found was that each element has its own unique line spectrum. It's almost like a fingerprint. And if you think back to things like our solving for things like empirical formula. We knew we had certain substances, but we didn't know what the compound was. This is one of the ways you can actually figure out what elements are present by looking at the bright line spectra of these different elements. So two scientists, Rydberg and Balmer, actually developed a mathematical equation to calculate the energies. These were purely empirical, so there were from observations they derived the formula. They did not do any experiments at all. Okay, and we're not going to get into the mathematical equation here right now. All right, so if we look at the difference between an emission spectrum and an absorption spectrum, let's first start up here with the continuous spectrum. So our continuous spectrum is like what we talked about. It is our Roy G. Biv, okay, and it is continuous. There are no breaks in it. We also have our emission spectrum, and you can see here I have these very discrete bright lines in the spectrum. So I don't see all the colors. I only see these little lines of light. Now, the absorption spectrum is kind of like the mirror image of this. So I have this line here with the emission spectrum, and notice in my absorption spectrum that matches up with the gap. So if I kind of marry the emission spectrum with the absorption spectrum, I end up with the continuous spectrum. Okay, so they're kind of opposites of each other, but they're also very, very important. Again, we tend to look at the emission spectrum and not the absorption spectrum when we're looking at different elements. Okay, so that's where we're going to kind of stop here for right now. And in my next video, we're going to start getting into quantum numbers and the quantum mechanical model of the atom, and we'll also talk about Bohr.